Good morning, good afternoon, good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking IBM for sponsoring today's event. IBM Analytics is an integral supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Semantic Research, Alteryx, Tableau, HPE Vertica, Dell Statistica, and Teradata, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. So today's webinar is entitled Apache Spark and IBM Streams Working Together in Streaming Analytics. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We'll have one presenter that I'll introduce in just a minute. There'll be 10 or 15 minutes of Q&A following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Jacques Roy of IBM Analytics. Jacques is a member of IBM Analytics' competitive and product strategy team, specializing in big data streaming analytics and Spark. And over his more than 30 years in the industry, Jacques has worked in many technology areas, including operating systems, databases, and application development. He's the author of multiple books, with the most recent being Streaming Analytics with IBM Streams. He's a contributor to IBM's data magazine, Big Data Hub, and Jacques also been a presenter at many conferences, including IBM's Insight at World of Watson. So thanks for being with us today, Jacques. We're looking forward to your presentation. Now, Spark is recognized as a great analytics engine. One of its benefits is its inclusion of machine learning algorithms that can group, predict, classify, and even recommend based on the analysis of a corpus of data. Once the model is created, it can be applied to new data. In some situations, there's a need to score the model while the data is streaming to decide what to do with the new data. So in today's Data Science Central webinar, we'll show how to process the data to arrive at a model and how the resulting model can be used to score streaming data using IBM Streams. So Jacques, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Well, thank you, Bill. So let's move on. So today what I'd like to do is talk to you about both Apache Spark and IBM Streams. To start my presentation, I will give a short introduction to what Apache Spark is and what IBM Streams is, and I will then talk about what how they can work together to get to a solution. Hopefully we'll be able to get to a demo. Just as we were going live, I was starting to have some problems with the demo, and it seems to be crashing on my laptop. So we'll see if we can get to that. So let's get started. So when we talk about Spark, I'm assuming some of you are familiar with it, but just in case, I want to make sure that I give a little bit of background so people are familiar with where Spark comes from and what it's used for. So some background here. It started as a project, a research project in 2009 and became open source in 2010. So it's a general purpose cluster computing system that is really targeting what MapReduce was designed for. Basically, it's a generalized MapReduce that allows you to process data, and instead of having a two-step process like in the MapReduce approach, it can have as many steps as needed, and because of that, it's much more appropriate for business problems that, of course, have more than two-step processes to get to a solution. So it's a batch-oriented processing type engine, and the main concept is immutable, resilient, distributed data sets, and some other constructs that are built on that. One thing I want to point out is the list on the right side. You can see here multiple versions of Spark that came out over time, and you can see that basically almost every month the Spark team comes out with a new update to the product, and every roughly 3 months or so, they come out with a major release. And so at the moment, the Spark 2.1 is the latest release that came out on December 28, 2016. I would expect a new update coming out shortly, a new major release. Okay, so let's move on. So when we talk about Spark, people tend to kind of say Spark and include everything that is talked about when we think about Spark. And so what you can see here is a chart that is a little bit more complex than the one that is usually shown, and I'll have the usual one shown a little bit later. And so you see multiple components here, and in the middle, in the processing engine, you see the Spark core. So when we talk about Spark, in general, we really talk about the Spark core and adding after that some libraries on top of it. And these libraries would include things like Spark SQL, Spark R, ML Lib, and also Spark Streaming. These libraries are very useful to provide a higher level of processing that makes people more efficient. And you can see there's a lot of other things that the Amp Lab had been working on, and it interfaces with other components that are not from the Amp Lab, for example, the Hadoop Yarn. I wanted to point out also that there's something that has been made available in open source called, it's the IBM System ML, now it's Apache System ML, and it's a library of machine learning library that IBM has put together over many years and decided to contribute that to the open source. The importance of this library is the fact that it does work with Spark. It can also use Spark, but the library takes it really a step further, where you're able to have you're able to use a runtime optimizer that will decide based on where the data is, what is the best way to execute the algorithm. And so that's really a very sophisticated library, and hopefully we'll see more and more integration between System ML and the Spark environment. Here's a slide that shows an interesting survey that was done two summers in a row by Databricks, basically the people that invented Spark, coming from the Amp Lab. And what you see is in the libraries that I mentioned a couple minutes ago, you have Spark SQL. I mentioned data frames here. I'll get to that in a minute. Streaming, ML Lib, and GraphX. And you see that really the majority of people are using Spark SQL. And in 2015, you had this division between 69% using Spark SQL and 62% using data frames, when in fact data frames are the building block for Spark SQL. And because of that, you can see that in 2016, you can kind of eliminate data frames from the survey because it's basically the same thing. But you see the large majority of people using Spark want to use SQL because it's an interface that allows you to define what you want to do as opposed to how to do it. And it makes people a lot more efficient. And that also tells us that really there are a lot of technologies that have been around for a while that are very relevant to today's world of big data. And so, but we also see that people use usually more than one library. One of them is streaming, Spark Streaming. what you have to remember about Spark Streaming is it's not really a streaming library. It's more of a library that simulates streaming but using microbatch. And it was actually an afterthought. When you look at Spark Streaming, Spark came out in 2009, open source 2010, and Spark Streaming came out in 2012, over 2 years after Spark was created. And really the idea was if you process a smaller amount of data, you can process it relatively fast. And if you submit your jobs let's say every few seconds, you can simulate a streaming engine. And if you read the documentation on Spark Streaming, one of the main idea behind it was really to provide a way to do basically ETL. And so, as I said, Spark Streaming is still batch, and it introduces an additional concept called the discretized stream that allows for that continuity between batch jobs, so it can pass information to the next batch job so you can continue the processing. One of the issues you have with Spark Streaming is the fact that it's still based on the RDDs I mentioned earlier that are immutable. So if you need to keep state information and you have, let's say, a list of 1 million devices that you're monitoring, and each batch job that comes through only changes 100,000 devices out of the million, which is 10%, you still have to copy the entire RDD into a new one for the next batch job. So that's part of the reason why when it comes to keeping state information, Spark Streaming has some issues. And of course, the Spark community is looking at how to reduce the overhead of Spark Streaming, of the RDDs, to be able to improve that. But you also have the fact that since you're dealing with batch jobs, the more batch jobs you submit, the more overhead it causes. An analogy to that would be when you look at network packets. If the data itself in each packet is very small, the overhead of all the other structures around it become a much larger percentage of the overall payload, which means that it becomes less efficient in terms of overall throughput. And that's a little bit what we see with Spark Streaming. Therefore, with Spark Streaming, I would strongly suggest that you look at that more in terms of looking at latencies that are measured in multiple seconds, so then you don't have issues of having the jobs being submitted faster than they can complete. Recently, as of Spark 2.0, a new streaming approach has been put out as alpha. It's still actually in 2.1. It's still experimental, which means still alpha or beta, and hopefully we'll see later this summer it will become a more production type level product, and it's called structured streaming. But structured streaming is still based on using under the cover the same streaming engine, which is basically submitting batch jobs and making everything available as data frames, which would then allow for an SQL type interface on top of streaming. And so because of that, we see that we have kind of an overlap between what Spark can do and what IBM Streams can do, which I'll introduce in a minute. And what you see is really Spark was designed for batch processing and is really good at processing data at rest, processing a large amount of data to get an answer and be efficient at it and provide constructs that allow people to work at a higher level and be more productive. Then as part of the overall libraries, you have Spark Streaming that allows you to do some sort of streaming, more ETL type jobs that require that basically doesn't require low latency, that can support multiple seconds latency and process the data, and as I said earlier, more as an ETL tool. And then you have IBM Streams, on the other side that basically that is able to process data in real time and process one event at a time, where when you're in batch mode, then you're time-based. You have your batches that are accumulate data in, let's say, 15-second interval, and then processes the data in a batch job, and then that could be appropriate. But if you want to work at machine speed, then you need something that's able to work and process the events and work at machine speed. If the data you're processing in semi-real time is for human consumption, then you work more at a human speed. Let's say you want to provide data to a dashboard. Then you know that your dashboard cannot be refreshed every half a second or seconds. You need to leave a little bit of time between refresh so people can really see what's on the screen. And so having a latency of a few seconds is appropriate for the dashboard. And in many other cases, latencies that are higher, that could even be measured in minutes, could be appropriate. So that's why you have in the middle that micro batch Spark streaming that in some areas could overlap with what IBM Streams can do. So I've been mentioning IBM Streams, so let's move on and talk about what IBM Streams is. So IBM Streams, you can look at it as three major components, and here it says acquire, analyze, and act. But I'm also using this to be able to talk about the engine itself. So you have to have an engine that is able to scale with the amount of data you need to process and be able to process it as fast as possible. So the idea of behind IBM Streams is to have that scalable engine that is able to do the analytics and be able to keep state information about what's happening, so it can take that into consideration as part of the analytics. And on the one side, you need to be able to acquire data from many sources. And for that, IBM Streams comes with a large set of libraries that adapters, I should say, that allow to read from different data sources, may that be databases, may that be Hadoop system, may that be message queues, HTTP type connection, REST API, etc. You can then ingest that data and process it, and on the other side, being able to act on the data and decide what to do with your data, either send it to a dashboard, write it to an HDFS file system, for example, or a database, or really end up taking actions at machine speed. When you take, for example, fraud detection, you don't want to have the action taken at human speed because the fraud happens at machine speed, and therefore you need to take actions to stop these intrusions, to allow people to react and decide what's the final action that needs to be taken without being compromised. So that's one example where in fraud detection, the faster you react, the faster you limit the damage. When you monitor machineries, you need to react also at machine speed, milliseconds, even microseconds in some cases, so you can avoid some problems. You can see trends, for example, the temperature in a machine going up and correlated with other sensors could indicate that there's a major issue, and if you can turn off that machine before it breaks, that could avoid multiple days of downtime by instead having the machine down for a couple of hours. And so machine speed reaction is very important. And in fact, in terms of performance, we've seen compared to other open source products that despite the fact that IBM Streams is a proprietary platform, a commercial product, it becomes very competitive compared to open source products that are perceived as being free. So in this case here, the small example I'm giving here is a benchmark that was done by Walmart, and multiple vendors were invited as part of that benchmark to benchmark some streaming engines. And in one case here, we see that Apache Storm, which was the premier open source streaming engine for quite a while, ended up performing very poorly compared to IBM Streams because of scalability issues. And that's where really the difference is. If you do testing of the streaming engine and you're working with small data sets and small ingestion, low ingestion, everything can appear to be fine, but that's when the load goes up that you see how the software reacts under pressure, that you can really see the benefit of it, where it can really take advantage, in the case of IBM Streams, really take advantage of the resources of the machine and optimize the utilization of these resources to be able to get to an answer. And in our case here, we saw that IBM Streams was 20 times better in terms of performance on the same hardware than Apache Storm. And when you take into consideration the total cost of ownership, just in the case of the performance, we see that the amount of resources spent on the hardware side is much higher than the overall cost when you can reduce the hardware, and even when you pay for licensing. So what IBM Streams is, it starts, as I said, here in the middle with a scale-out runtime. But what's also important in these types of situations when you want to create solutions is to have pre-built functionality. And that's one of the benefits that we saw of Spark compared to MapReduce, where Spark came with a set of classes that allowed programmers to come up with a solution much faster instead of just having the framework that says, okay, well, do what you want to do. Here's a framework. It had these classes already there that you could take advantage and get to a solution. And then by having an SQL interface on top of it, made people even more productive. So in the case of IBM Streams, what we have here on the right side, we have the analytic toolkits that are included with the product. And these toolkits are packaging of functionality that allow you to solve a specific problem domain. So for example, if you're dealing with geospatial type processing, you can take a look at the geospatial toolkit and take advantage of the functions in there to do geofencing, for example. If you're dealing with databases, you look at the database toolkit to be able to take advantage of how to access databases through simple interfaces. And if you deal with message queues, again, you have a toolkit that has multiple operators that allow you to easily read and write message queues, different message queues, may that be Kafka, RabbitMQ, or others. And so that's important to have this functionality already available so you can be more efficient at creating solutions. On the other side, on the left side, we have integrated development environment. So that's another aspect that is pretty important, where if you have the proper tooling to create your solution, for example, if you have an editor that understands the syntax of the language you're using, it allows you to get to solving your issues faster because the editor points out the errors you may have in there. In the case of IBM Streams, we even have a graphical editor that allows us to drag and drop operators on a canvas and connect them together, and then edit the parameters of the the operator, so we can set them the proper value. For example, if you have a filter operator, you edit it and change the filter condition by simply entering the condition that says, I'm looking at this attribute within my record, which we call tuple, and I want that value, if it's greater than 10, for example, then send the record through one output. If it's smaller than that, then send it to another output. So that would be a very simple change to make to your environment to say, well, I'm adding a filter, drag and drop from the streams that's coming in, and be able to continue on that front. So that makes people a lot more productive. And in addition to that, we have monitoring tools that allows us to monitor the health of the entire environment of the cluster and see where how the flow of tuples goes through the entire set of operators, and that would allow us to easily detect bottlenecks, for example. So having all that tooling makes people a lot more efficient at getting to solution, makes basically companies more agile to adjust to the needs of their environment. Okay, so IBM Streams has multiple toolkits, as I said, and just to give you a quick idea, we have things like the time series toolkit, geospatial toolkit, rules toolkit, that's an integration with the IBM Operation Decision Manager, the mining toolkit, we have integration with SPSS, voice to text, R project, and Spark ML Live toolkit. And that basically leads us to how does IBM Stream integrate with Spark. So there's multiple ways you can integrate with Spark. One of them is the fact that since Spark deals with data at rest, Spark itself, I'm not mentioning Spark streaming quite yet, that means that if we have the proper adapters to be able to write to these repositories that Spark needs to access, it's one form of indirect integration. So in this case, we have the database toolkit, HBase toolkit, HDFS, and JDBC that gives us that type of integration. And of course, we have other integration with Object Store and Cloudant and so on. So that would be one approach to the integration. When we look at Spark streaming, what we see is that Spark streaming has a limited number of data sources available, sources in sync, which means the data sources is what you read from, the sinks are the outputs where you write to. And since there's a limited number of data sources and sinks available, you could say, well, streams could be simply an adapter that will read from the data sources that are not supported and then pass them through to, let's say, Spark streaming to a Kafka queue, for example. But it goes further than that because in some cases, as I said, if you want to react at machine speed, Spark streaming cannot do that. So Spark could be used as a processing engine for real time and then passes on the information, aggregated information, for example. Less time-sensitive processing can then be passed on to a Spark streaming that could then integrate with some of the other parts of Spark. So that would be another approach that could be used in this case. So I just mentioned that. So the reason why streams should be used as an aggregator is because Spark streaming has the main issue is the latency, as I said. As part of the documentation, in the latest documentation, they seem to have removed that statement, but still it was there for so long that it's probably a marketing decision to remove it. They said they claimed that they had Spark streaming would work well for latency of half a second, but it's much higher in practice because, in fact, when they talk in that same paragraph where they mentioned that, the next sentence was saying, but start with 15 to 30 second latency and low volume and go from there to see how much you can reduce the latency. And the reason for that is that when you get to a point where the processing time required goes a bit higher, the only way you can tune it is really by reducing the latency. So you're kind of stuck because there's a limit to how much parallelism you can put within a stream of data coming in to pass it on and divide it. And so IBM Streams could be there to provide latency in milliseconds or lower and keep context information and pass the data in a either aggregated format or pre-processed format to Spark streaming that in a format that's more appropriate for that engine. So as I said, streaming and analytics and actions in streams aggregation for Spark streaming. Another way to use streams is to use it as a scoring engine. So you could develop some models using, for example, Spark machine learning, and these models would then be developed using historical data, basically, as it says here, data at rest. And once the model is created, you can pass it to the Spark ML Lib toolkit, basically an operator, a set of operators, to be able to score your model through a live stream. And that's basically what's easily done through IBM Streams, since we have an operator that simply takes a few parameters, one of them being here's a model that we're using, and here's the attribute that contains the data that you need to score, and then can pass the result and take actions. Okay, so briefly here, as part of the Spark ML Lib toolkit, you see that we have a dozen operators for the scoring, and of course we can refresh the model within IBM Streams as the people in charge of the system decide that they need to refresh the model, and then the scoring becomes stays relevant. So here's an example. As I said at the beginning, I'm very sorry. It turns out that my my virtual machine that was running my demo had an issue, and at the last minute the issue showed up, and I'm unable to run it. But I'll explain what can be done. So as an example of document classification, you can use the naive Bayes algorithm, that is a supervised learning, and you collect data. In my case, I'm using an RSS feed of Computer World articles, and I collected data over multiple weeks, and I prepared a document by extracting the text of the article from an HTML page, normalize uppercase, lowercase, eliminate stop words. Stop words are words like the, this, in, at, etc., and hash the words into numbers, create a sparse matrix that can then be scored, and export the model. So the reason of all that processing is because you go from, for example, in my case, I had 716 documents as input, and I go from, in terms of number of words, 382,000 words, and when I eliminate the stop words, it falls down to 189,000 words, and when I remove the distinct I kept only one copy of each word. You see that we have, at the end, only 16,000 words to deal with, which means that when you do hashing, you can do that over a certain number of buckets that is very limited, because in reality, the number of different words is limited. And even if we get a few collisions, it doesn't really interfere with the classification. So in terms of modeling, there's a few concepts that are important that I want to mention very briefly, since I don't have, since my demo failed me. You have things to consider like term frequency. So what that means is how many times a word is found in a document, But then you have the inverse document frequency, which is how many documents a word is found in. So if you have 716 documents and you have a word that is found in all 716 documents, that word becomes irrelevant in terms of doing classification. And so that's why these concepts are important. And so you need to pre-process your documents using these techniques to be able to weigh the words appropriately. And the reason why I'm talking about this is because when I read a document in real time, I need to be able to do that type of processing within Streams. And since Streams is extensible, in my case, what I did is I simply wrote a Java operator. A Java operator can be added to Streams with just a few annotations to standard Java code. And with that, I was able to use the exact same algorithms that Spark used because I included the Spark jar file as part of my environment and be able to then do these term frequency and inverse document frequency exactly the way Spark did it. So that means that when I finish processing my document, I can pass it on to the scoring operator, and it has exactly the same thing that it would have if it had been done straight from Spark. So there's multiple mapping that needs to be done. So category mapping, in my case, I had 12 categories, token, hashing, etc. I will skip this part briefly and export the model. So the application that I have, again, I'm so sorry I can't get to that, basically uses a list of RSS feeds and passes it on to two operators here. You see at the bottom the graph. By the way, this graph comes straight out of the Streams development environment. When I talked about the graphical editor, that's exactly what I have, where I dragged and dropped my operators and connected them with the arrows there, where the read RSS operator here reads the RSS feed, passes the documents to the next operator, the read HTML, that processes the HTML document to format it appropriately so it can pass it on to Spark naive base. And then I do multiple other things, including, in my case, in my demo, I was doing some text analytics to extract important terms and important sentences that I had in there. And go from there. So this demo, despite the fact that I can't do it here live right now because of issues with my VMware image, I made it available to everyone, so you could actually download the code, download the VMware, a brand new VMware image, and install the demo there. It comes with instructions, and you could actually run it yourself and see the integration between Spark and Streams that way. So, bring the demo. In conclusion, when we think about IBM Streams and Apache Spark, we can't see them as competing technologies. We have to look at them as complementary technologies where Streams provide the ability to do in-context streaming analytics at a very high rate and very low latency that then can take advantage of Spark processing, either by being able to score models coming from Spark or by being able to feed data to repositories that Spark use, or even aggregate data and reformat the data in an appropriate format to even pass it on to Spark streaming. So there's a lot of possibilities in terms of integrations between the two products. Hopefully, with the way I described IBM Streams, you can see that it's really a high-end, basically a premier streaming analytics products, high performance and low resource consumption, as demonstrated by the benchmark that was done by Walmart, and that really could augment your environment to get a proper solution, so you can do the real-time processing in addition to the more traditional data at rest type processing that you would then use with Spark, for example. And since Streams has a rich development and administrative tooling, it makes people very productive with that graphical editor to drag and drop operators, put them together. There's actually a language included as part of of Streams that is very easy to learn for experienced programmers. It looks very familiar, but it's also possible to write code in Java, Python, and other languages for people that are more familiar with that. And since Streams has an extensive number of toolkits, you can quickly get the solution. So with that, I'd like to pass it back to Bill for the Q&A.
Well, Jacques, thanks for that excellent presentation. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We've had a lot of questions that have come in during the presentation, so we'll do our best to get through all of them in the time remaining. And during this Q&A session, I'll leave up this screen with contact information for Jacques if you'd like to contact him following today's webinar. So let's get started. Jacques, just to start, is IBM Streams a new IBM product?
Bill, yes. I did not mention that at the beginning. I kind of went very quickly in terms of what IBM Streams is. IBM Streams actually started as a research project back in 2003. But the research project was between the U.S. government and IBM Research, and the requirements were to have an engine that is high performance, very scalable, and can process any type of data. And an additional requirement from the government was that they didn't want to be in charge of maintaining the product, so they wanted to make sure that IBM would have plans to make this product a commercial product. And so in 2009, that's when IBM Streams was released as a commercial product, and since then it has continued to be improved, and we are currently at version 4.2 of the product with a large customer installation in different industries that includes, for example, telcos, and even in the IoT world, we have several automobile manufacturers that are using Streams.
Oh, well, thanks for that explanation. Now, the audience would like some clarification. Do I have to install both IBM Streams and Spark? In other words, does IBM Streams ride on top of Spark, or can it be separate?
Okay, let me see if I understand the question properly. So do you have to install both? In the case of the operators, the operators that we provide, we actually include the Spark jar file in there, so you don't have to install it to be able to do your scoring. So they could be installed separately in different environments. So that's not an issue.
Okay, so IBM Streams incorporates portions of the open source Spark. Am I getting that correct?
That's correct. So for the operators that are needed, that are included in the product, we also include the ability to have a Spark. But the installation of Spark would be pretty simple. You just simply get that jar file and make it available. But yes, so it can be separate.
Okay, thank you. And an audience member has asked if you would please explain data frames in Spark. Is that something that's even relevant to Streams, or is that only relevant to microbatch environments?
Okay, so Spark came out with the concept of RDD, as I mentioned earlier. And over time, they developed an additional concept that builds on top of that, the RDD concept called data frames. And what data frames provided is a more structured approach to processing your data. And so as part of the data frame object, you have methods that are more SQL-like on top of it. Currently, for IBM Streams, we use this, in terms of, back to that scoring idea, we use the Spark ML library that relies on RDD. It would not be difficult to move to the Spark ML as opposed to ML Lib. There's been some movement there, so we're kind of waiting for the dust to settle. So for us, it does, since the integration is about scoring these specific models that use RDDs, then the data frames are not relevant. And in terms of the other types of integration that I mentioned, like passing data to Spark streaming or writing to repositories, then the idea of data frames is, or even data frames and RDDs are really not relevant at that point.
Okay, I got it. Now, just more questions about comparing IBM Streams and Spark. For example, does Streams support all the Spark operators, or perhaps it supports operations that Spark doesn't even have?
Oh, wow, that could be a very long discussion. I'll try to summarize here. So IBM Streams is it's a separate product. Therefore, it has a large set of operators that are made available to do all sort of processing of the streaming data that comes in. And so there are, I'm sure, operations that are similar, but it's not the same concept. The idea of Spark is always set processing. You think about an RDD. An RDD is basically a data set, like the name mentions. And so you have some set operations involved there, where Streams deals with events, basically, with records that come in one at a time, and again, what we call tuples. And so at that point, you process that record that comes in. You can keep track of what happened before, can keep state information, and we have what we call windowing type operations that allow us to then process based on a number of records or an amount of time or a delta between the records that pass through. So the operations are different. It's not a clear answer here, but bottom line is, if you wanted all the operations that are provided in Spark, which, as I said, is somewhat a little bit mismatched because it's set processing compared to one record at a time, you can easily include that within Streams, like I did in my demo, where I created a Java operator that used some of the classes that are provided by Spark to make sure I was using the exact same, for example, hashing algorithm that was used by Spark. So I could easily provide that type of processing, include that type of processing if needed, but with all the toolkits and operators and functions that are available in Streams, I doubt that people will feel the need to do that.
Okay, thank you. A question about database compatibility, and let me break this into two parts. First of all, the streaming data that is passing through temporary storage in Streams or Spark, can that move on to an Hadoop database? But more meaningfully, you and I both understand that particularly scoring in streaming environments, we frequently have to combine the stream data with static data from a Hadoop database. So the question probably is best stated, are there any limitations on the types of database from which I can draw data in order to score data on the fly?
The short answer is no. There are no limitations. But, I would like to qualify that a little bit. So IBM Streams comes with a set of adapters. I did mention the database adapters, so that means if you're thinking about using data that comes from a relational type database, you have the adapters that would allow you to enrich the records that are coming through in real time. So then after you enrich them, then you can maybe score them better because you added the appropriate information. We also have adapters for, again, that was part of the presentation I mentioned very quickly, for HDFS, HBase, and others, which means that most repositories, I did mention also Cloudnet, I believe, and some others. Most repositories, we could enrich our records that are coming through by accessing data through these repositories. There would be optimization techniques that could be applied to cache some of that data in memory so we don't have to go back all the time. And at the other end, we can easily, these same adapters are both for reading in and writing out, so I can write out to all these types of databases at will. So the compatibility is there. IBM Streams is a in-memory analytics engine. So in terms of repository, it's really up to what the solution designer decides to do in terms of enriching the records and writing back to a repository. But many adapters are already there. If for some reason you have a new type of adapter that we don't support quite yet, you may be able to either find it on GitHub, because we have a large set of other toolkits that are open source on GitHub, or you can easily write your own, for example, by writing a simple Java operator that would access that new type of repository.
Well, thank you. Thank you for that answer. Back early in the presentation, you compared IBM Streams to Storm very favorably. Are there similar benchmark numbers you can talk about comparing IBM Stream to Spark streaming?
I should have expected that question. So we did internally have a benchmark, and actually we did publish it. But one of the main issue is that we come out with a benchmark, and of course it's favorable to Streams. And in fact, in that specific benchmark, we put a latency of 30 seconds just to make it easier for Spark, where for us, a latency of half a second would have been much better, because then Spark streaming would have had so many jobs queued sequentially that could have caused some problems. And even through that, IBM Streams was showing that over the scalability curve, in terms of you add in terms of throughput, you add in terms of how many things you need to keep track of, that IBM Streams was much better at doing this. The issue with these types of benchmark is really related to the first slide I showed about Spark, is the fact that they come out with new releases almost monthly. And so it's very easy for them to say, well, yes, but we've done some improvements, and so we're much better now. So I don't have numbers with, for example, Spark 2.0 or higher. And but as I said, I think that the guideline would be look at what is the two main guidelines to start with would be, what is the latency you need to achieve and how much state information you need to keep. And that could show that the project could be in danger if the latency is too low if you were to use Spark. And of course, in terms of development time, in terms of all the analytics that are provided in Streams, Spark really doesn't have that. You have to go find the libraries that would give you that analytics. I talked a lot about MLlib, the machine learning algorithms that are there, but in terms of analytics, there's a lot more that is involved, and IBM Streams has a lot of capabilities. So there's a lot of things to consider, but in terms of benchmark, again, difficult to compare, because it changes so fast that they always make these huge performance improvement claims based on the fact that they remove some limitations from a Java virtual machine. So we don't have current numbers. IBM has pushed for a while to have a standard benchmark, but as you know, establishing a standard benchmark that is accepted by the industry can take a long time. So
Indeed, indeed it can. Well, thanks for that explanation. Interesting question from an audience member who asks, if I already have a streaming application, how difficult is it to integrate IBM Streams on top of that in order to take advantage of some of these benefits that you've talked about?
I don't think I can answer that question. I would actually suggest that person gets in touch with me for more detailed discussion, because what does that mean that they already have a streaming application? So I don't know where they're starting from and what the processing is. In the case of, you say you have a streaming application, you want to go to IBM Streams, it's a new environment. And depending on what processing you have there could be a one-to-one match where you say, oh, I'm filtering here, so I'm adding a filter operator. But it's most likely a rewrite of the application. Not that it would be necessarily a difficult thing to do or time-consuming thing to do, but without more details, I can't comment further than that.
Well, that's fair. And a similar question that perhaps is related is, does IBM Streams have a graphical user interface, a kind of a drag and drop, as some of these products do, that makes implementation of those filters and operators a little more easy to see?
Yes. Like I said earlier, as part of the tooling, currently we have an Eclipse-based tooling that gives us a text editor, but also a graphical editor. And basically what you have is you have your list of operators that are available that you can simply drag and drop into a canvas and connect them together, and then make some small modifications to the operator. Let me make a comment about this also in terms of when I say you can change the parameters of an operator. You hear a lot about API economy and API interfaces, et cetera, et cetera. Personally, I find APIs difficult to use because often, let's say, for example, you can say, well, I have an API to use Kafka. Well, if you have an API to use Kafka, then also then you need to learn about also the details on how to use that API and how to connect to your queue. And there could be some subtleties there that you're not taking advantage of, or that you misunderstand, and that can take the learning curve can take a while to make you proficient enough to feel that you have an efficient implementation. Okay, that can be days, can be weeks, who knows. When it comes to operators, when I talked about you change a few parameters, it's that simple. It's the fact that you identify where your message queue is, you identify a couple of other things, and there you go, you have access to your message queue. Same thing for databases, same thing for a lot of different adapters. So, for example, another example, text analytics, I'm able to simply say, well, I have my text analytics extractors that I created, let's say in Big Insights. I can take them as is and put them in Streams and simply say, here's the attribute I'm operating on in terms of my text analytics. Here's the extractor that I'm using, and there you go, you're ready to go. So the ability to change parameters on operators makes people a lot more efficient than having to find an API and then learning which of the classes and which of the methods are appropriate to use to get your solution.
Well, Jacques, thank you so much. Those were great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Jacques and the IBM Analytics team so they can follow up with you after today's webinar. I have just a few quick announcements. If you would please mark your calendars for April 18th. That's our next DSC webinar, which will be Accurate Anomaly Detection with Machine Learning by Anodot. Also remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of datasciencecentral.com in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to IBM Analytics for their sponsorship, and our speaker today, Jacques Roy, for his insight into today's topic. My name is Bill Vorhies. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on April 18th. Have a great day.